All right, gang. More on the central limit theorem. I find that kind of perfecting this technique, applying the central limit theorem and getting the correct answers and probabilities. Sometimes it helps just to throw all the problems in and kind of force us to determine which process, whether it's proportions or means, and test the assumptions whether or not the normal distribution is even applicable. So let's just run through these. First problem, and this handout you'll have in the resources for this lesson. So a waiter believes that the distribution of his tips is positively skewed with a mean of $9.60 and a standard deviation of 540. What is the probability that his next party will tip him more, $20 or more? Same thing as at least. We can't do this problem. No can do. Because the distribution is positively skewed. I mean, it's so tempting to go over here and, go to stat and go to calculator and come down to normal, but we don't have a normal distribution, so we can't use that key or that option in the calculator. So what is the probability that the average tip, so once we get into average tip, we're getting into the central limit theorem, for the next four parties will be at least $10. Can't do this problem. Drive me crazy. Because our sample size isn't 25 or 30 or larger. When we have a positively skewed distribution, a non-normal distribution, remember our sample size has to be pretty large. And really, I'll tell you, in complete transparency, 25 or 30 is marginal. It works a lot better when you get up around 100. But the 25 to 30 simulations are really, really close to the normal distribution, so we can get a pretty good approximation on the calculations. Now, what is the probability the average tip for the night will be at least $12? He served 32 tables, so we have 32, which is greater than 25 or 30, so we can proceed. So the normal distribution will apply. The mean is going to be $9.60. The standard deviation will be $5.40 divided by the square root of the 32 tables. And we want to know if his average tip will be greater than or equal to 12. So the probability here would be 0.0060. Still, a pretty low probability that, and again, it kind of makes sense because the average tip is $9.60, so 12 is quite a bit higher than that. All right, number two, state police have found that 70% of drivers traveling on a major interstate highway exceed the speed limit. Guilty as charged. They plan to set up a radar trap and check the speeds of 80 randomly selected cars. If 60 of the cars are speeding, what is the value for P and P hat? Well, P is our probability, our percentage from the population. So that's going to be 0.70. And our P hat, I'm not going to go into my editor, will be equal to the 60 divided by 80. That's our sample. And that's just what, 0.75? 6 divided by 8? Yeah, 0.75. So are the appropriate conditions met to use the central limit theorem to find? So what we need is N times P. So N is 80 times P which is 0.70. And that's going to be 56. So that's higher than 5. And we need 80 times 0.30, which is 24. And that's greater than 5. So the appropriate conditions are met to use the central limit theorem. So if the appropriate conditions are met to use the central limit theorem, what's the probability that the police catch 60 or more of the 80 speeding? Well, this is a classic normal distribution problem. So the mean is 0.70. The standard deviation is the square root of 0.70 times 1 minus 0.70 divided by the total number of cars. And we need to know if catch more than 60 out of 80. Or you could put 0.75 there. So the answer here would be 0.1646. All right. Now, let me tell you where students mess up a lot. I see this a lot where students will come in there and just put the 60 right there, and they'll compute it and they get something crazy. We have to understand that the 60 is out of a sample size, because 60 out of 80 is completely different than 60 out of a million. So you have to provide the point of reference, the point of context there, and include how many you've actually sampled. Because again, this is a p-hat, right? And as I told you in a previous, demonstrated in a previous video, p-hat is x over n. So we have to have the x and we have to have the n. Now, if you want to go ahead and, put the 0.75 in there, take the x divided by n, just simplify it, then yeah, it's cool. That'll work. But you can't not include the total sample size. All right, carbon monoxide emissions for a certain kind of car vary according to a normal distribution. That tells me that my sample size only needs to be 2 or larger. With a mean of 2.9, standard deviation 0.4. What's the probability that a randomly selected car, so just one, has carbon monoxide emission greater than 3.2? All right, so no fancy stuff here. 2.9. Put the standard deviation in there at 0.4. We want greater than 3.2 because this is a mean problem. We don't have to worry about that other stuff. So 0.2267. I'm not going to type that there. You can see 0.2267. What is the probability that n equals 17 cars have an average carbon monoxide less than 2.75? Now we get into a point where we have to divide by the square root of the sample size. Again, have a normal distribution, so 17 is bigger than 2, so it works. And we want less than 2.75. Compute 0.0061. Now, the next thing says 15 cars are selected at random. Calculate and interpret the z-score. And we haven't got into z-scores yet, so this is one of the purposes of this video. All right, so what I want to do is I want to make this. So let's calculate the z-score. So guys, remember, a z-score is just the x minus the mu over sigma. That's the way we've done z-scores previously. But when our sample size, I'm sorry, that's not right. When our sample size is greater than 1, 2, 3, 4, 5, 100, whatever it may be, notice that we get into a standard error and not just a standard deviation. So we have to make the difference. So the object of interest is no longer a single score we give with x. Our object of interest is the sample mean, x bar, minus the mean mu over the standard deviation. So I can calculate the mean. So for C, average emission level 3.5. Mu is 2.9. And I need sigma, which is 0.4 over the square root of 15. All right, so let's put this in our calculator and not do anything goofy. So I'm going to put 3.5 minus 2.9 in parentheses. And then I'm going to divide by, in parentheses, 0.4 divided by the square root of 15. Now, there's what I did in my calculator. Notice that I made sure everything in the denominator is in parentheses because I don't want a order of operation issue. And notice that I put everything in the denominator in parentheses because I don't want a order of operations issue. So the z-score is 5.81. And remember, for something to be unusually high or unusually low, we use this threshold, this cutoff of 2. If it's higher than 2 or lower than -2, so this is clearly bigger than 2. So yes, we have unusually high score. All right, a new academic achievement test has been developed that has a mean 320. Standard deviation is unknown, but research indicates that a score of 250 is located at the first quartile. What's the population standard deviation? Let me grab another sheet of paper on this one. These are kind of cool. This question actually showed up on a midterm exam, or a final exam, I'm sorry, in one of my classes. So what would we do? Well, the first thing I would see is that, this whole z-score, if we don't have enough information from a raw distribution of these academic achievement tests, we can always bounce the information off of a z-score. So what do I know? I know that a z-score, I don't know why I closed that, mean 0, standard deviation 1. That's the mean and standard deviation for z-scores. I know the z-score that represents the first quartile. First quartile has 25% of the distribution below it. Is negative 0.674. The value from the distribution that represents the first quartile is 250. The mean is 320, and the standard deviation is unknown, right? So this is over 1, so all I have to do is multiply both sides by sigma. $250 minus 320, we can just do that in our head, is negative 70. If not, just grab a calculator, divide both sides by negative 0.674. The sigma is going to be so 70, negative 70 divided by negative 0.674 is 103.86. All right, let's try it out. See if that's a plausible answer. So in our distribution of scores, it has a mean of 320 and a standard deviation that we're proposing of 103.86. Score 250 is a Q1. Now, what should my answer be if this is reasonable? What percentage of scores should be below Q1? 25%, right? All right, close enough for me. So 103.86 would be the standard deviation. That's fun, right? All right, a bank has found that 7% of the people who receive loans will not make their payments on time. The bank has recently approved 200 loans. What is the probability that over 10% of these clients will not make timely payments? All right, the 7% right here, I'm going to highlight that. What does that tell me? That tells me I have a central limit theorem for proportions problem, right? So what do I know? So this is for number 5. So what do I know? I know that my mean is equal to P, which is equal to 0.07. I know my standard deviation is P times 1 minus P over N. So it's going to be the square root of P, 0.07. 1 minus P, 1 minus 0.07 is 0.93. And how many customers were there? There were 200 loans. So I'm just going to throw this in the calculator. So 0.07 times 0.93 divided by 200. And I get 0.01804. All right, let me show you what I got right there. All right, let's work the problem. The mean is 0.07. The standard deviation is 0.01804. I want over 10%. Compute. The answer would be 0.048. All right, last question. A recent poll, which was conducted in August 2010, 12 years ago. Wow, that's crazy. Found that I don't even know how to put much stock in this. In fact, I wouldn't put any stock in it because it's 12 years old. Well, I'm constructing these videos in 2022, so really outdated, but we can still calculate some stats on it. So 80% of Americans want prayer in school. Assume that we randomly select 1,000 Americans and 760 say they want prayer in schools. Find and interpret the z-score. All right, so this is just really a question of can you, do you know what p hats and p's and n's and all that, what does it stand for, right? So I know that in this problem that the p is the statement about all people, so that's going to be 80%, 0.80. I know that my p hat is going to be from my sample, x over n, so it looks like they sampled 1,000 Americans and 760, which is going to be 0.76, state that they want prayer in public schools. See, to me, from a statistical perspective, what I think would be far more interesting would be a multivariate study here to get into political and religious affiliation, see how all that's related. But right now we're just keeping it simple and just looking at this data. All right, so Z is going to be the p hat, 0.76, minus the p, which is 0.80. And then on the bottom, we need the 0.80 times 1 minus 0.80 over the total sample size, which is 1,000. Now, if I can put that in my calculator without doing something goofy, I get negative 3.16. And just to give you an indication what I did, I can get the entry and show you. So 0.76 minus 0.80, again, I always put that in parentheses so I don't have an order of operation problem, then the square root of 0.8 times 1 minus 0.8, 0.2 divided by 1,000. And again, important, notice that all of what's under the square root sign should be there. I think what happens a lot of times is students they'll get this confused where, only part of it is under the square root, but that's a different problem. That's like a Phillips screwdriver and a straight screwdriver. Two different tools, two different types of problems. All right, gang, that's all I got.